Hey guys, it's Mr. Wolf here. Sorry I can't be in class today, but I'm going to be using this video to go over the notes that I went over at first period and the notes that I would have gone over with you guys if I would have been in class today. Alright, so we're going to be looking at target 3 today. And so it's a pretty wordy target, so I want to just point out some important points. This idea of mechanical energy that we're going to be looking at, and that there's types of mechanical energy. Those main types are going to be kinetic energy and potential energy. All right, not only that, but we're also going to be looking at this idea that within a system that energy is conserved, and so this is going to be fairly similar to momentum. And so this is just a brief overview of what this target is going to look like. All right, so here's some key terms to kind of keep in mind for target 3. And so kinetic energy and potential energy, I'm sure you guys are already pretty familiar with. And basically the potential and kinetic energy added up together are going to be our mechanical energy. And then finally we're going to be looking at the law of conservation of energy. And finally here are some new equations we're going to be using. This one is going to be for potential energy. This one is going to be for kinetic. And of course remember that 9.8 meters per second squared is going to be our acceleration due to gravity. All right. So energy. Energy is and by the way, go to page 13 of your physics packets. So energy is the ability to do work, and this is at the top of your page. And we talked about this before. And the amount of energy something has is the amount of work that it can do. The unit of energy is going to be a joule. Right? And this makes sense. Remember, in the back of your page, we had that idea of this is your system. Right, and this is our environment, and work is just putting energy into or out of the system. Right? And so remember we talked about this example as also using money. And so if we're going to measure money in a dollar sign, right, when we spend money or put money in the bank, we're also going to be using a dollar sign. So we use joules when we talked about energy going in or out. So whether it's in our environment or within our system, we're going to be using joules as our measurement for energy. All right, so what I want you guys to do now is go to that back page of your packet, and we're going to continue some of those notes that we did on Monday. So here's the environment. Work is just energy going in or out of our system. All right, but we talked about our system also as if it were a bank. Okay, and so when we have money in a bank, we could have that in different forms. We could have that maybe in cash, or savings. Right? And when we have energy within a system, we could also have that in different forms. So I like to think of cash as kinetic energy. All right, so it's going to be energy in motion, just like we're going to be spending cash easily, while savings is more of stored energy. So we're going to be calling that potential energy. All right? And so the cash plus our savings is going to equal that total amount of money in our bank, and kinetic energy plus potential energy is going to equal that total amount of energy within our system. So another way of basically saying that this total, the energy of our system, is we're going to basically call this the total mechanical energy. Alright, and so you guys have all this stuff written basically from right now and Monday. I'm going to have you guys start writing what I'm going to be doing next in the next blank space below this general diagram you guys have here. So just like we have our total sorry. just like we have our total amount of money, that's going to equal our cash plus savings. Right? Doesn't matter how much cash or savings we had. The total, if we add those up, it's going to equal our total amount of money. So we could also have our total mechanical energy, which is going to equal our kinetic energy plus potential energy. Right? And this is going to be the total mechanical energy of our system. Right? And so if we draw a line from kinetic energy, and then I'm going to go to a new blank page, but it'll basically just be an arrow for you guys, and you guys can start writing about kinetic energy. Again, this is going to be on the back page of that packet. Right. So again, we're going to be talking about, we had that arrow coming from kinetic energy. Right. Kinetic energy is energy in motion. So if an object is in motion, it has kinetic energy. Right. Our equation for this is going to be kinetic energy is going to equal 1/2 mv squared. Right? So the m is mass and the v is velocity. So the more mass and velocity an object has, the more kinetic energy it has. And again, we're going to measure this in joules. All right, so imagine above on your sheet you guys had potential energy here, so we're going to draw an arrow, and I'm going to go to a blank slide, but you guys are going to continue writing on this back page. All right, and so when you do work on an object, you add energy to the system. Okay. Now, if this energy, I'm going to just add to system. Right. If this energy can be stored, we have potential energy. All right, and so again, just continuing on with the notes for potential energy. Potential energy is energy stored at a height. And it's going to be an interaction between the object and Earth. Okay? And this will, and so energy stored at a height, interaction between an object and the Earth. This will bring us to our equation. So our equation for potential energy is going to be, and we could also represent potential energy, we could call it gravitational potential energy. And we could also represent it as a U, with a little g right here, so for gravitational potential energy. And our actual equation for that is going to be mass times gravity times height. All right, so let's look at an example of potential energy with this equation, mgh. All right, so we have three different examples, and so in each example, the object, even though it's in newtons, it's all on Earth, so they're going to have the same mass. All right, they're both on Earth, so they're going to have the same amount of gravity. Really, mg is a way to equal their force, and is a way to measure their force in newtons. So it's really their force times the height above the ground. All right. And so in both instances, even though the object just went up here, went up the ramp here, and went up here, all right, they all went up the same height. So the potential energy of all of these objects is going to be equal. So let's go to one last example for this video. I'm going to have you guys skip some of those problems at the bottom of 13, and if you guys flip to page 14, this is where this problem starts. So we have a 100 Newton boulder. You lift a 100 Newton boulder 1 meter. So it's always good to just draw these out. All right, so we have the boulder, it's 100 newtons. Lift it 1 meter. And so it asks how much work is done on the boulder. Remember, work is just how much energy goes into or out of our system. And so let's look at beforehand. Our system is going to be the boulder. And so before, it's at a height of 0 meters. And so if we're using potential energy equals mgh, if we have a height of 0, our energy in this situation is going to be at 0 joules. So our initial system is at 0 joules. So how much work is done on the boulder? Let's just solve that using our classic work equals force times distance, right? Which is going to be equal to 100 newtons times 1 meter. We're going to get 100 joules as our work done on this. And it's going to be positive 100 joules. We've put energy into our system with this work. So what power is expended if you lift the boulder in 2 seconds? Remember, power is going to be work over time. So we just have to do 100 divided by 2, and we're going to get 50 watts for our power. Right. So then it finally asks, what is the gravitational potential energy of the boulder in the lifted position? And there's a couple ways we could go about this. If we understand what work is, it's how much energy we put into the system. Before it was at 0 joules, and we lifted our boulder up to this height. Right? Before going into this equation right here, we calculated that we put 100 joules of energy into our system, into our boulders. So our potential energy should equal 100 joules. Well, let's go about this with the equation as well. Right? So UG is equal to mgh. UG is equal to this mg right here is really the object's weight, right? Mass times the acceleration due to gravity. And we already know that. That's 100 newtons. We're going to multiply that by the height. And so our gravitational potential energy is going to be 100 joules. Right? And it's just going to be 100 joules. It's positive 100 joules here is because this was the work being done. We added it into our system. All right. So this basically concludes it for this video, but what I want you guys to do really quick is go back to page 13 and complete those 2 problems where you have to find the kinetic energy and the potential energy. Shouldn't take too long at all. All right, and so I'm going to make one more video. The next video is going to be on conservation of energy.